photometric selective plus candidates at redshift 9 to 10 in the JWST Cosmos web feed. Cosmos web feed.
Okay, thank you, Tavi, and then your team, and then all the organizers. It's my great pleasure to be here. Today, I want to introduce my master student Kostas' recent paper about selecting protoclusters from the Cosmos Web JWST field. Before starting, I want to, in addition to Kostas, I want to thank all the collaborators, all the people in my group, and then also Hashimoto-san's group, and then other collaborators, including people here. Okay, so let's get started. So why protocluster is important? Well, KJ already covered a lot of them, but I want to remind a few. First point is understanding cluster evolution. If I remind, maybe everybody knows, but the galaxy clusters occupy only less than 1% of the volume of the universe, but in terms of mass content, it's more than a quarter. So it occupies a big fraction of the mass of the universe. Then, if you see a massive cluster monster like this, you wonder, what was the progenitor? How did it evolve? And then we want to study for the cluster like this. That's first point. Second point is that to understand the galaxy evolution in very dense environment. In galaxy clusters, galaxy density is sometimes 3 orders higher. So galaxy evolution in such a dense environment may be different. Star formation may be morphology different, and also there may be more merger and interaction between galaxies. And there may be a quasar feedback, agent feedback, if there's a massive agent at the center of clusters. So we want to study galaxy evolution in different environments. So this is a metaphor. In a rich environment like Academia Sinica here, and in a poor environment like University, the galaxy evolution may be different. So you want to see the difference. Okay, and then the other reasons KG covered, I think, this compare with the simulation models, and then study the galaxy evolution, cosmology, and also there may be a contribution to cosmic reionization if the galaxy number density is 3 orders higher, and then maybe star formation rate is higher in protoclusters. So we want to study. There are a lot of studies to do with protoclusters, so protoclusters are important. Okay, then I want to look at a little bit of history. So pre-JWST, we didn't have very deep near-infrared, so we stick to the I-band dropouts from the ground-based telescope. So this is my previous work using the superatom on Super telescope, searching for I-band dropouts around the massive quasar at redshift 6.4, and we found a protocluster. So there are 7 Lyman-Gray galaxies around this quasar. This was, I think, one of the most distant protocluster at the time of this writing. And then later, there came Hyperspranka, so we were able to search much larger volume for protoclusters, but still searching for I-band dropout. This is Hariganes-san found many protoclusters at redshift 6. I helped a little bit on this work. So that was the situation. But then JWST changed the situation. With the JWST NIRCam, we have very deep near-infrared photometry, so we can extend the protoclast searches to redshift 7 and beyond. And then for people, this very competitive area, so people have found a few protoclusters already. So this one is at redshift 7.6, behind a famous lensing cluster, so 1, 2, 3, maybe 8 galaxies behind the lensing cluster, so that's redshift 7.6. Another example here by Morishita-san at redshift 7.8. This is again also behind a massive lensing cluster, able to 744. This is not a protocluster, but this is a protocluster. You know that, right? Okay. However, as you see, these are individual examples. Still limited number of the protocluster is small. I think the largest one today is this Genetor 24 that search protoclusters in Sears field, which is only 100 square arc-minute. So what we want next is we want the statistical search. We want a large volume. Okay. Then JWST Cosmos Web is suitable for search for protocluster in large volume. Its total area it took almost 2,000 square arc-minute. So this is 20 times larger than the Sears field. So that's a very good field. So that's why we search for protoclusters with my master student Kosas. So Kosas is a very good student. As soon as database Cosmos Web data is released, he reduced the database Cosmos data by himself. He's fighting with the bugs of the database pipeline, and he was very good at coding. But at this time, only half of the Cosmos data when he started was released. So in this work, we only use half of the Cosmos data. But still, this is 100 times, 10 times larger than the CSV. Okay. Then how do we find protocluster? It's very simple. So we have now near-count very deep interphotometry. So we look for F115W dropouts that corresponds to redshift greater than 9. And then we connect these dropout galaxies with friend-of-friend algorithm within 2.54 megaparsec. So if galaxies are within 2.5 megaparsec, they are considered as friends and they connected to be a group. Within photometric redshift areas. And then select high-density regions greater than 3 sigma. That's pretty simple. This shows you that, so these are database photometry. Yeah. And then here's so this blue line is F115W. So at redshift of, so in this case, this is redshift 10. It's very faint here. It's a dropout, and then it's bright in 150. So this is basically how we search redshift 9 and 10 galaxies. And then the selection method is already established. This is competitive field. Many people try to select out the 115 dropouts. So it's sort of color box, it's already established. So we use this example by Harikani-san. So if 115 dropouts comes around here. The review of our paper asked us to check if the selections are okay using Jade's spectroscopic galaxies. And then, well, it's not perfect, but most of the redshift 8, 9 galaxies are in this box. So that's good. And then after we select dropouts, we do density fitting. So this is one example of such galaxy, and it is nothing, and then bright. So that's a typical dropout. And then we fit the SED and then estimate the photo. See, in this case, 9 points something. Okay. Then we calculate the density using that friend-to-friend algorithm. And then we found 7 protoclusters between redshift 9 and then 11. We selected structures with greater than 3 sigma significance. Something like here. This is between redshift 9 and 10. And here. And this is 10 to 11. And then we found 2 protoclusters here and here. If we still need spectroscopic confirmation, but if confirmed, it's the most distant protoclusters ever found. I show you some examples. So this is one of the structure with 3.6 sigma, and over density is 9 times over dense than the field average. And then as you can see, these 7 galaxies are close to each other with photometric redshift probability is something like this. So this is something 9.5 or so. Another structure here. This is 4 sigma significance with over density of 8. And then again, this one is almost 10 galaxies, around redshift 9.5 or so. Another example, this is 4 sigma with over density of 8. There's 8 galaxies here with again 9.3 or so, redshift 9.3 or so. Last example is this one is 3 sigma, and then over density is 8 times, and then again redshift 9.3 or so. So we find 7 of these structures. And then we look at the, okay, thank you. So we try to look at the, okay, I think Keiji said that, thank you very much. The same thing, all these protoclusters need to be connected to the redshift 0 structure. That's what Keiji said, I'm proud of that this slide. So this is trying to estimate the halo mass of these protoclusters by adding all the stellar mass of member galaxies, and then using the beta Bernoulli, the stellar mass to halo relation. And then, well, this is a rough estimate, but it comes somewhere around here, 10 to 11 and so. And then the evolution in the simulation goes something like this. So at redshift 0, these this corresponding to 10 to the 15, that's something like a comma cluster mass. Okay, so far so good. But then next step is, as I said earlier, we only use the half of the Cosmos area. And now we are collaborating with a Taipei JWST group led by Claude and Jack Dai, DC, and Wei Hao. And then they did a very advanced data reduction of the whole JWST Cosmos web data. So in collaboration with them, I'm looking forward to extend the search to the entire Cosmos region. Okay, and also spectroscopic follow-up is also necessary to confirm the structure. Okay, and then paper it's just accepted. We're going to post it to associate students, so please pay attention. Okay, I stop here. Thank you very much for listening.
2 more minutes, but thank you. Okay, so questions? Yeah.
Tomo, very interesting talk. Did you have a chance to look at the structural properties of those galaxies, the protocluster candidate galaxies?
Oh, structure of galaxies?
Yeah, morphologies or the specific kind of index properties, anything like that?
Not yet, because we are not so confident about member galaxies yet. If I go back here, how do I go back? I'm sorry, I finished. Can you present this slide? Yes, sir. Okay, thank you. So we're not so sure about all of these true member galaxies. For example, these members are a little bit voltage offset. So I think spectroscopic confirmation would be nice. And once we know spectroscopically if they're really protocluster members, then it'd be very interesting to look at the structures and properties of these protocluster galaxies.
Okay, thank you.
Thank you for a good question.
Okay, any other question? So the typical number of galaxies associated to each of density is like 4 or 5 at most, right?
Well, in this case, there are 7, yes.
7 galaxies?
Yes.
Okay. But typically, I showed in the map, the number of the galaxies associated to each.
Right.
Is like 3, 4. So it's a kind of group.
That's true. Yeah, it can be called group.
Close to a rich cluster.
Right.
Yeah.
Well, then at this redshift, the number of galaxies is already low, so all the protoclusters, including previous work, are something like that. I found a paper found 2 galaxies and they called it protocluster.
And also, do you see any environmental dependence where, the over-density regions tend to host more bright galaxies, for example?
That's a very interesting point. We haven't looked into that yet, but that's definitely interesting.
Right.
Hi, Tomo. Thank you for that. I was wondering what the uncertainty is on just the contamination from dusty galaxies, just because it's at high redshift and you're only using broadband photometry.
Right. Oh, yeah, that's always a concern. When you select droplet galaxies, they might be dusty galaxies at low G. Well, at least these I forgot exact criteria, but I think we throw away that if I think probability density distribution is larger in lower Z, we throw out those galaxies. So that's why our member galaxies all have these very high Z for the Z probability. At least we did that, but yeah, that's a very concern.
If we can take another question. Yes.
Just a very naive question. What's the relationship between delta and sigma?
Oh, the sigma is significant, so we put a random aperture and then see how significant is this structure. And then delta is over density, so compared to average density, how many times density is higher? So it's similar but a different indicators.
Right. But like for the next example, you have
It's-
delta lower but with higher sigma.
Right. So
Right.
because the aperture size and the photo G errors are slightly different in each candidate. So these numbers are slightly different. Thank you.
Okay, let's thank Tom again.
Thank you very much.
Next speaker will be Sujin Kim from SNU, and she's going to tell us searching for dark structures.